Hello, all. Here I am recording this for the second time. The first time I finished, and I had a file with 3 kilobytes. So clearly that wasn't it. Well, here we go. Here's the exam review for the second exam. Just let's go over the exam ideas first, quick. Remember, there's two parts to the exam. On part one, there's 20 multiple choice items, followed by 10 fill in the blanks, and the 10 fill in the blanks come word for word from those study guides. Remember, you complete part one, and in part one you use nothing other than your head, what's in your brain. You complete part one, you'll get part two. Part two, you can use anything in the world you want except internet-enabled devices and, of course, each other. Okay? And remember, you need to complete both of these parts in 1 hour and 15 minutes. Okay, so now, show your work. Okay, I cannot give partial credit if you don't show your work. If you just put a completely wrong number on the line, what do I know? It's wrong. For all I know, you were 90% correct. Well, I would love to give you credit for that. Okay, you know who I'm talking to, right? Okay, the first item on here. In a population of scores that has mu equals 75 and sigma equals 14, Sally had a score of 54. Okay? So now what's going to happen is they're going to transform the distribution of scores. And this is a fairly common thing called normalizing. And so what's going to happen is they're going to change the entire distribution so that it has a mean of 500 and a standard deviation of 150. And it's not really hard to do. It's really quite a simple thing. And the key to this question here, though, is realizing that if Sally got a z-score is a z-score. It doesn't matter what the raw score population numbers are, the z will always be the same. Okay? So in this situation, if we can calculate Sally's z-score in the first distribution, then all we have to do is take that z-score, bring it to the second distribution, and figure out what the raw score would be in that one. Okay? So take a look there. I've drawn that first distribution on the left, the original raw scores, centered at 75, standard deviation of 14. And you see Sally's score falls way down there at the bottom. She's kind of a not such a hot student there. And so you see her 54. When you calculate a z-score for Sally, it had better be a negative, right? And a negative, even larger negative than -1. So let's pull out our old z-score formula. Z equals x minus mu over sigma. Grab Sally's score of 54 minus a mean of 75 over the standard deviation of 14. Do the math on it, you get -1.5. Lovely. So now, in this new distribution, which is in the middle here, it's centered at 500. Look at that, 150 on each side. This z-score of -1.5, what raw score will pop out at that point? And so we grab our old equation, x equals mu plus z sigma. And so we put in 500 plus -1.5 times 150 and do the math and get 275. All right, very good. Easy enough, Sally. All right, scores on an oh my goodness, these are like brain dead easy. I hope. Okay, I hope. Oof. This is chapter or lecture. Let me see, 7, 6, 5. This is the very first lecture, the very first simple thing we learn. And so, what is z-score? No, step back. Mu is 457. Sigma is 145. So what do we get? The raw score associated with a z-score of 0.8. Oh, I see. A z-score of 0.8. So we just take the equation, x equals mu plus z sigma. I know the z-score. I want to know the x-score. There's the equation. So I pop in the mu, 457 plus -0.8 times 145 and just get 341. Lovely. What is the z-score associated with the raw score? Okay. And so now I've got a z, I want a raw here, or no, I've got a raw, I want a z, so we just pull out our old z equation here. Z equals x minus mu over sigma. So the score involved is 564. Take away the mean of 457 over that standard deviation of 145. 0.74. I round it up. 0.7349. What is a raw score associated with z of plus 2.3? It's really just the part A, just asking it again, right? Get your equation out. And if memory serves, D is really nothing more than a version of B. Pull your equation. So hopefully, these are not tricky for you. Okay, so this one is a little tricky. Okay? Let's read this one. A researcher knows that the average weight of American men between 30 and 50 is mu equals 182 and sigma 28. The researcher would like to determine if men who have heart attacks between these ages are heavier than the average male. For a random sample of 25 heart patients, body weights are recorded. The sample mean is 174 with a standard deviation of 24. Are these patients significantly heavier than the population? Test with alpha is 0.01. Alright, so taking a look here, we have a known population with a known standard deviation. We have drawn a sample of scores, and we would like to know if this sample of scores is different from the population. This is a classic z-test. We've got everything smells like a z-test here. Okay? So, what I've done here in this problem, and you're going to see this same kind of layout on the next test especially, where we're going to cover the independent t, the related t, and the one sample t. Yeah, 3 different t-tests. And so it's a way to try to pull partial credit out of your knowledge. Alright, so I've broken up the problem into steps which are perhaps showing me what you have. So, state the appropriate hypotheses. Number 1, is this a one-tailed or a two-tailed test? And remember, we got to look for a words in here. And the word that is screaming out at me is heavier. So that word is implying I'm looking for a one direction only, not two, one. Okay? So let's start with that alternative hypothesis. And that simply says the average weight of men that have heart attacks is greater than the average weight of all men. Okay? And that's kind of what the researcher was asking. And so the null hypothesis simply incorporates these two outcomes, right? The average weight of men that have heart attacks is either exactly the same as all men or even less than all men. Okay? So what formulas are involved here? And let's just make sure we put down the equation to show your knowledge. So we know that we need to calculate the standard error. So sigma sub x bar equals sigma x over the square root of n. We know that we need the z-test. So z equals the sample mean minus the population mean over the standard error. Wait, I missed something here. I missed something? Oh no, I see. Haha. I just put it funny. Okay, there we go. Part C. What is the critical values? Alright, and I know this is one where we get tricky, but remember now, alpha is 0.01, and we want to know heavier. So we need to know what is the z-score that separates that top 1%. What sets off the top 1% from the bottom? And so we know that when we look in the chart, we will never be able to find that 1%. Okay, it just isn't going to be there. Instead, we'll be able to look up the distance between this point I'm interested in and the mean, right? We can look up 0.49. All right, we can't look up 0.01. We can look up 0.49. And if we do, we would come up with, see, now I came up with a really specific number there, 2.326. But I think we worked with this one the other day, and we settled on 2.33. So We'll settle on 2.33. It's close enough, okay? Close enough. So for these data, what is the obtained value? Oh, wait, 2.33, yeah. And so that 2.33 sets off the region of rejection, right? So thinking ahead, if the z-score or the z-test, when we compute it, obtains a z-score that is in the region of rejection or to the right of that point, then we would reject the null, right? So here we go. For these data, what is the obtained value? So sigma sub x bar is the mu of 28 over the sample size of 25 equals 5.6. Okay. The z obtained then would be my sample average of 174 minus the 162 of the population and divided by the standard error of 5.6. We can calculate that out. We get 2.1428. Wow, I'm very specific. Okay, 2.14. Okay? Now, moving on to the last part of this question. No, that's not the last part. This. Where are you? There. This is the last one. And so here I have three, I've laid this out. Your decision based on, the null and in words. So really there's four different statements I'm making here, okay? The obtained value of z is in fact less than. You see the 2.14 falls to the left of the critical value, okay? So z obtained is less than z critical. We could say z obtained does not fall in the region of rejection. Okay, these are different ways to state it. But the two that you really need to say to get this answer correct is fail to reject the null. We fail to reject the null because our obtained z-score does not fall in the region of rejection. Now we need to make a conclusion. We need to, what does this mean? So you fail to reject the null. It means if men having heart attacks are not significantly heavier than average. Okay? That's what the outcome of this thing is. Now, I want to point out one thing on this problem because it's there for you. In this one, there's a little bit of a sneaker trick. You see there down towards the bottom of the thing there, it says body weights recorded, sample mean of 174 with a standard deviation of 24. And in the z-test, you do not need that 24. There's no need for it. There's no use for it. It's interesting information. It's lovely, but there's no place to put it in the z-test. Ignore it. It's a trick. I'm telling you, it's a trick, okay? There's no reason for it. Later on, maybe that's going to be useful. Trust me, it might have some uses later. But it's just an absolutely useless piece of information for you. Do not see that one and try to desperately find a place for it. Okay, good. A random sample of size n are drawn from a normal population having a mean of 80 and a standard deviation of 12. What proportion of the sample means will be between? Lovely. So they're basically asking three of the similar questions. So let's get through this kind of methodically, okay? There's three different questions. But as you notice in these three different questions, in the first one there's a sample of 9, in the second there's a sample of 32, and the third there's a sample of 16, okay? So let's start out and just, let's get those standard errors. Because for the three questions here, you're going to need a different standard error because you have a different sample size. And so for the first one, as you can see, standard error equals, there I go, the sigma of 12 over the square root of 9 and get 4. And in the second one, sigma sub x bar equals, again, the 12, but now over the square root of 32. The sample size to get 2.12, and in the bottom one, sigma sub x bar equals 12 over the square root of 16. Is that what it says? I'm sure it does, right? Yeah, square root of 16, and we get 3. Okay, so we get three different standard errors, and hey, there you go. And taking a look at the pattern here, it shouldn't surprise us because we find that as the sample size goes from larger, as it goes from 9 to 16 to 32, we find the size of the standard error going down. And that matches up exactly to a lot of the different exercises we've been doing in the lab. Okay, so that's good. So now, we've got this thing, we'll hold it off to the side. We want to know, okay, we've got raw scores, and we want to know proportions. Oh, poop. In order to go from raw scores, or raw averages in this case, in order to go from these sample means to z-scores, no, sample means to proportions, we need to stop at z-scores in the middle, okay? So let's calculate the z-scores for all of these important points that they have on here, okay? So on the first one, the two important pieces of information are the 74 and the 86. Let's turn those into z-scores, okay? And so in the top one, remember the standard error is 4. So z equals sample mean minus population mean over standard error. So the sample mean is 74, or the sample mean of interest is 74. The population mean is 80, and it's the 4 in the bottom. So we get a negative 1.5. The second number of interest is 86, right? So we get the sample mean of 86 minus the mu of 80 over the standard error of 4, and we get a positive 1.5. Ah, that sounds like it might be useful. In the second one, there's only one important number to work with. We're only working with greater than 83. So let's find the z-score for 83 in this one. Okay? We're going to do the same thing as the first one, but of course now we need a different standard error because the sample sizes are 32. So again, we'll take this sample mean of 83, take away the population mean of 80, and take it over to new standard error of 2.12 to get a 1.42. Got it. Last one. What proportion of 16 between 77 and 82? So let's calculate those z-scores. And so you've got the mean that I'm interested in of 77 minus the population mean of 80 over this other standard error now of 3 to get negative 1. And the 82 corresponds with 82 minus 80 over 3 equals 0.67. And so you see what I've done here is now that I've got these critical, or these important z-scores rather, is I've drawn a picture. And so let's start with the top one. In the picture you can see I've already wrote the answers there, so pretend you don't see the answers, right? You can see what is there is those two important points that are at positive 1.5 and negative 1.5. And your job is to figure out what proportion of scores fall between positive and negative 1.5 z-scores. Okay? So clearly we know that when we look this up, we can't look up a single number here, right? There's no such thing because our z-score chart tells us the distance between a z-score and the mean. So let's look up that 1.5. So we'll go down. I got the chart up in here. I'm looking at it on my screen, and you all have it up in front of you. So going down the left column until you get to the 1.5, and going over to the very first column, because it's 1.50, we find 0.4332. So between 0 and 1.5, it is 0.4332. Between 0 and negative 1.5 is also 0.4332. And so the answer to this question, what is the proportion between those 2 points, is a combination of those two. 0.8664. Put them together. Lovely. Next one. Now we've got that 1.42. You see I drew the picture. It's kind of a funky picture, but you get the, I hope you get the idea. And so what do we find here is we want to know what proportion is to the right of 1.42. Okay? And so we know that we can never look that up. Instead, we can look up what is the proportion between 0 and 1.42. Okay, so let's look that up first. I go down the left side to 1.4, go over to the first, second, third column, get 0.4222. Okay, so to the left side of this number of interest, it's 0.422 until the mean. Well, we know that each side of the distribution is 0.50, and so to get the answer we want, we need to take 0.50 minus 0.4222 to get the 0.0778. And finally, we've got another one here. And this one looks awfully similar to the first one, okay, in that you're going to have to calculate two different areas. But the only difference in this one appears to be that the z-scores are different, and therefore you're going to have to literally look up two different numbers. And so what was the first one we cared about? -1. So we go down the column until we find 1.0 on the left, and stick to the first column because it's 1.0, and find 0.3413. Okay, and I've already drawn it on the image there. 0.3413 of the scores fall between -1 and 0. The other number is 0.67, so we go down the left column, 0.6, and then across 0.7, map them out, 0.2486. Boy, I hope that's what it says. Yeah, I think it says that. 2.2486. And so the answer to this question is simply to put together those two outputs, 0.2486 and 0.3413, I think I just said, to get 0.5899. All right, good. And now the last one. Scores on a course exam are normally distributed with a mu equals 80 and a sigma of 8. Teacher wants to give the top 20% of the class honors, a grade of fail to the bottom 30%, he's vicious, and the grade of pass to the remaining 50. Okay. What are the scores that will cut this apart? Okay, let's take a look at this picture. So we'll look at the image here, and you see what I've got when I draw these dashed lines? I need to find what is it that will break this distribution into a 30, 50, 20. That's basically what it is, right? The entire distribution equals 100. I want to know how can I break this up so that 30% fall to the left, 20% fall to the right, and 50% fall in the middle. So we're going to look on our z-score chart to find what these z-scores associated. So now we know that when it comes to this -1, here's the deal. We are able to look in our chart and find the distance between score and the mean. Now I'm looking at the left side, the negative side. And so we want 30%, but to get the answer I'm really looking for, I really need to look for 20%, right? The distance between this score and the mean. And so we need to look in the chart until we find about 0.20. And so let's see, I'm going in here, 0.52, 0.53. What am I settling on? It's somewhere between 5.2 and 5.3. Look at that, I put -0.52. I would be okay if you put -0.53. It would have been a fine answer. Either one would have been fine. -0.525 would have been fine. What do I care? They're all okay. Okay? So now, interestingly, let's go out to the other side. In order to calculate or figure out the z that's going to set off the top 20%, we need to know the z which has 30% between it and the mean. Kind of a funky little thing there. And so when we look this up, we go up to the charts and we find, see, there is no 0.30, but there really is something fairly close, a 0.2995. And so if I go to 0.84, there it is, that is as close as I'm going to get to 0.30. Okay, it's kind of close. And so there's the z-scores that would set off those different scores. Now, what raw scores will set that apart? Heck, you now have a very simple, go back to lecture 5 and use the old x equals mu plus z sigma equation. And so you've got two of them. X equals the mean of 80 plus negative 0.52 times 8. Get yourself a 75.84. And X equals 80 plus 80 plus 0.84 times 8 to get an 86.72. And so what this is saying now is, looking at the actual answers there, if you have a score less than 75.84, you fail. If you have a score between 75.84 and 86.72, you pass. If you have a score larger than 86.72, you get honors. Okay? So, this is all this is. This is not, don't make it harder than it is. It's not that hard. Remember that just like on the first exam, the real exam will be awful similar to this. I mean, it's not going to be the same, but it's going to be awfully similar. All right, it was the last time, and it will be this time. So make sure you got yourself organized. Make sure you do not run out of time on this test. Okay, have your notes organized. Wear your glasses so you can see the z-score chart. You know who I'm talking to. All right, so be sure you're ready for it. I'm going to have Mrs. Amaripa being proctoring this thing. I believe she's going to. Things could change. So remember the deal. No cell phones ever. Any point in that exam, anybody see, and she is sharp as a whip. I'm telling you, she will catch your ass, but you wouldn't do it, so it won't matter. Okay. So I will hopefully see you next week, Tuesday. Okay. Have a good week.